So far, every variable we've made has been under a few constraints. The most important of these is that the data's lifetime is static. This means that at compile time, we can point out exactly where the variable is created and where it is destroyed, and it can never exit its scope. But what about these examples? At the top, we create a variable int x equals 5. In a new scope, we create a variable int y equals 3, and we set x equals to y. At the bottom, we create a function y that creates a variable y equals 3 and returns y. And later on, we create a variable x, and we set that equal to the return value of y. It turns out that in both these examples, y never actually leaves its scope. Its value is just copied into x. It's a very subtle difference, and in this case it doesn't really make much difference. But with more complex types, it can be much more important. For example, look at the following. At the top, we create a vector of type int x, and then in a new scope, we create a std vector of type int called y. We resize y to have a lot of elements, and we set x equals to y. And at the bottom, we create a function y that creates a vector, resizes it to be really, really large, and returns that. And then later, we create a std vector of type int called x, and we set the value of that equal to y. Again, the value of y is copied into x, but this time it's a large object instead of just an integer, so you can imagine that it might take a long time to copy. In this case, it's important to be able to get the actual object out of its containing scope, and not just a copy of the object. So, what if we want more complicated lifetimes for our objects, so we don't have to copy data around when it's unnecessary? Enter dynamic memory. So, what does that even mean? Well, it means that you have memory, data, that isn't directly tied to the scope it was created in. Instead of being controlled by the scope directly, its lifetime is controlled by the lifetime of the views that are used to access it. Ideally, when no views are able to access the data anymore, it should be destroyed, and its lifetime should end. Now, when I say views in the data, you might be reminded of the idea of pointers or references from last week's videos. If so, you're absolutely right. The objects that allow you to access dynamic memory in C++ are called smart pointers. Like normal pointers, they allow you to access data with a lifetime that isn't necessarily the same as the pointer itself. Unlike normal pointers, the lifetime of the data is controlled by the lifetime of the smart pointer, or smart pointers, plural, that are able to access it, so two conditions will always hold. A smart pointer is always connected to either a valid object of dynamic memory that's still alive, or no data at all. And second, a piece of dynamic memory always has at least one smart pointer pointing to it. Let's see what this looks like in practice. There are two types of smart pointers: standard unique pointer and standard shared pointer. All smart pointer related content exists in the memory header file. Smart pointers are templated with one parameter, the type of the data that they should own. By default, smart pointers are null pointer, just like the null pointer for normal pointers, which means that they don't point to any object and cannot be used. Before we get into the nitty-gritty of using smart pointers though, a brief warning. While dynamic memory can be much more flexible than regular variables, using it brings a performance penalty with it. While this can be worth it to avoid copying around a huge amount of data, dynamic memory should really be used sparingly. A good rule of thumb is to default to regular variables and only use dynamic memory only when you run into a situation where you actually need it. In addition, most STL data structures, in fact every single one other than std array, already uses dynamic memory, so you should be able to use them without worrying about smart pointers. Now with that out of the way, let's look at some code that uses smart pointers, line by line. Here, we create a standard unique pointer of type int and we call it x. Right now, x is just null pointer. Let's assign it something by using makeUnique. So here, we've assigned x, std makeUnique int 5. So now x points to an integer. What happens if we set x back to null pointer? Well, x becomes null and points to nothing. And the data that it was previously pointing to is destroyed because it has nothing pointing to it now. The same thing happens if you let x go out of scope. Because x no longer exists, the data it pointed to is once again destroyed. So, what if you want to get the data out of the scope? First, let's try what we did earlier. We create a standard unique pointer called x, and in a new scope, we create a standard unique pointer y, assign that a value of 5, and then set x equals to y. However, this is actually a compiler error. What's the issue? Well, it would create two views into the data. X and y would both be able to access it. But unique pointer assumes that there's only one view that should be able to access the data. So this is a really bad idea. Instead of doing the wrong thing, the compiler just errors out and tells you to fix your code. It can be fixed like this, where instead of setting x to be equal to y, we set x to be equal to std_move y. Now std_move doesn't do anything on its own, but when used in an assignment, it tells the compiler that it is allowed to transfer data from y to x, resolving the conflict from earlier. It's a lot simpler in functions. When you return a smart pointer, the compiler already knows that you aren't going to use it anymore, so it doesn't need to move anything. We can just return the smart pointer directly. So, what if x is reassigned to some other piece of data? The old data will be destroyed. In general, if you have a question about what will happen in a certain case with unique pointers, it can be answered by remembering that every pointer will always correspond with a single piece of dynamic memory, and every piece of dynamic memory corresponds with one pointer. In some cases though, you need an object to be accessible by multiple owners, and you don't know which one is going to live longer. So the lifetime of the data must last as long as either of the multiple pointers to it exists. There is no unique accessor that's able to safely control the lifetime of the data without having some cases where the data does not live long enough. In this case, you would use shared pointer. Imagine you have many components to your program, each of which needs to access the logger object. Then, your diagram might look something like the following, where you have multiple components, and they each have a logger that is a view into some other logger object. Well, we can achieve this by using shared pointer and make shared, similar to unique pointer and make unique. Let's try and go through what's happening here, step by step. So, here we've created 4 components, A, B, C, and D, and in a new scope, we've created a new shared pointer of type logger, and by calling make shared, we've created a logger in dynamic memory, and the logger variable is a view into the logger that we've created. Afterwards, when we call set logger on A, B, C, and D, because shared pointer can have multiple views pointing into it, unlike unique pointer, we don't get any compiler errors, and now each component has its own view into the logger. After we exit the scope though, even when the original owner goes out of scope, as long as there exists at least one view into the data, it won't get destroyed. And now, instead of the previous example, let's say that A, B, and C all go out of scope, and only D is in scope. The logger still won't get destroyed because D still has a view into the data. Only when D is destroyed will the data get destroyed. Now, you might be wondering, shared pointer seems to be better than unique pointer. Why don't we always use shared pointer? Well, there are 2 reasons. The first is that shared pointer is slightly slower than unique pointer. But the second, more important reason is that it's easier to understand what's going on when you know that an object only has one owner. Shared pointer can have multiple owners, but with unique pointer, there's only one owner. And that makes it easy to understand what's happening in your code exactly.